Hello, this lecture is on product architecture. Product architecture is one of the newer topics in product development. Academic researchers just recently started thinking about this. People in the industry probably have been thinking about it for a longer time, but without some of the formalities and constructs introduced by research, such as architecture, interaction, decomposition, modularity, and integrality. So, these are definitions that are relatively new and started to become part of the standard language built around product architecture. The way I would like to present this is, first, to give you a sense of where the architecture issues and decisions fit within the overall product development process. Then review definitions of architecture, modularity, modular design, integral design, and so on. Then talk about some of the issues in selecting an architecture. Finally, we will do a little exercise about recognizing modular and integral architectures and to what extent real products fit these definitions. Architectural decisions are made upfront in the early phases of the product development process. Platform decisions are made at the product planning phase. Part of product planning, if you recall, is thinking about what would the platform be. Is there an architecture that we will inherit, or do we start from scratch and build a platform, or is it one-off product? In the concept development phase, we make decisions about the overall arrangement of the functional elements, which may determine the architecture, even though we may not actually finalize and formalize the architectural decision until we decompose and design and do the system engineering in the system level design phase. We define the product architecture as the arrangement of functional elements into physical chunks which become the building blocks for the product. Functional elements are the subfunctions that implement the overall functionality of the product, as we have talked about when constructing function diagrams. Physical chunks, on the other hand, are physical elements or components or a collection of components that are used to implement these different subfunctions. So the architecture becomes a mapping between functions and physical modules. A one-to-one mapping constitutes a modular architecture, while one-to-many mappings constitute varying levels of modularity, including integral architectures. Let me define those two terms further with a simple example. This is an architecture for a trailer. These are functions for the trailer. These are 6 of them listed. For example, protect cargo from weather, connect to vehicle, minimize drag, and so on. Here are the physical elements used in building the trailer: box, hitch, fairing, bed, and so on. Observe the one-to-one mapping between the physical elements and the functional elements. An alternative mapping is an integral arrangement, which looks like this. These are the same 6 functional elements as before, but now they are mapped to a different set of 6 physical elements. Notice that it so happened accidentally that these physical elements are equal to 6, just like the previous example. However, they could be 10 or 20. What's important here is the mapping between the physical elements and the functional elements. Observe how these same 6 functions are implemented by the physical elements. The protect cargo, for example, this functional element is implemented by 3 different physical elements: the upper half, the lower half, and the spring slot covers. The lower half also implements 3 different functions, or helps in the implementation of 3 different functions: protect cargo from weather, support cargo tools, loads, and suspend trailer structure. So you can see this many-to-many mapping between functional elements and physical elements. Then what defines the integral modular architecture is the complexity of this mapping. There are 3 types of modular architectures. All have one-to-one mapping between functional elements and physical chunks. However, the difference is in the way the chunks interface to each other. For example, in the slot modular design, all chunks are attached to a bus module, but the interfaces for these modules and the bus are of different type. Notice that this is a triangular interface, square, and a different interface here. You cannot interchange them. A radio and climate controls in an instrument panel is a good example of that. A bus modularity, on the other hand, chunks mount to a bus, but they are interchanged as the interfaces are the same. Square interface, different modules interface to this bus module with the same exact interface. An expansion card for a laptop is a good example. Finally, the sectional modular design. In a sectional modular design does not have really a bus at all, but the elements amongst themselves can be arranged in various different ways, creating variety. Let me show another simple example. What product is this? You might think it's a nutcracker, a telegraph, or a spot welder, but it's really a nail clipper. Can you comment on the architecture of this nail clipper? The top one exhibits modularity, obviously. The bottom one is integral. In what ways the upper clipper exhibits modularity as compared to the lower one? In the upper clipper, each physical element implements a function. The spring implements the pushback open function. This is where you push, right here. This is where you hold a keychain, for example. These are the blades. Maybe they are sharpable or replaceable. And the bottom design, in the integral architecture, you can see there are fairly few parts. To be exact, 1, 2, 3, and derivative 1, 2, 3, 4, maybe derivative 5, something like this, compared to much more parts in the modular design. And each of these parts implements several functions. For example, here, objects can often become so ubiquitous that we no longer question their form. The testimony of time shields such relics from the scrutiny and skepticism that we subject new products to. Nail clippers, for example, have barely changed since the Industrial Revolution, which is really strange considering the mess they can often leave us, your nails, in, and the fact that they spray your cuttings everywhere. This new company is out there that is trying to change all of this. They are calling this the ultimate clipper. The idea is to re-engineer the cutter so that the pressure is applied directly on the nail and catch the cuttings as you go. First, let's talk about modular architectures and give a few examples. Then we will talk about integral architectures with some examples. Then we will talk about choosing between them. Modular architectures are architectures where chunks implement one or a few functions entirely, and interactions between chunks are well defined. And by that I mean, maybe I just refer back to the earlier example here. Imagine I want to change the blade geometry here. In the modular design, in the upper nail clipper, then I will have to just change those two parts to change the blades. In the lower design, which is the integral nail clipper, I would have to change these two parts, which in fact relate to other functions. So interactions between functions would come up if I want to make changes in the integral architecture. Finally, modular architectures have advantages in simplicity and reusability for a product family or platform. It allows us to have product families without having a tremendous amount of production complexity and cost. What are some of the disadvantages then for a modular design? Perhaps they tend to be bulky, maybe increased cost because you're designing each module separately to perform a specific function. Any other disadvantages that come to mind? Here are a couple of examples: the Swiss Army knife and the Sony Walkman. Swiss Army knives have huge variety. They have hundreds of different combinations of blades that could be put in. This little blade with this larger blade is one single module, and they always come together. Similarly, the can opener with the other bottle opener screwdriver combination is also a single blade, and those two blades always come together. Then in this particular one, they added the pliers and the scissors. The second example is the Sony Walkman. You can also you may have also noticed that the Walkman have a huge variety of models, and if we explore the architecture of the Walkman, we can see how actually they have done it. I've got a picture of one Walkman taken apart. There are three main modules for the Walkman: the casing, the circuit board, and the tape drive. This is the casing here, and it implements the functions that deal with controls, user interface, radio and tape, and enclosure. This one has an analog radio, but you can imagine there are others with digital radios, solar power, and all sorts of different arrangements and colors. This is the circuit board, which implements specialized electronic functions that are specific to each model. But circuit boards are fairly easy to design and cheap to produce in low volumes, so they can make these in low volumes of hundreds or thousands fairly efficiently. The last thing is the tape drive mechanism, and it implements the mechanical functionality. It is actually very hard and incredibly complex. It includes belts, pulleys, and screws and bearings. There is probably 100 parts in here. The tape drive mechanism can be shared across the platform for all the high and low end Walkman models, which might be 50 different models. So they will make these in high volumes. So that's the key in the figure, is to figure out what's the hard part and tool that up and make it in high volume. Then the easy part you can make it more specific and make it in low volumes. Integral architectures have the generalized opposite definition. It is an architecture where functional elements are implemented by multiple chunks, or a chunk may implement many functions. It is an arrangement where interactions between chunks are poorly defined. So if you were to make a change to one chunk or function, it may have effects on other chunks or functions. Perhaps more importantly, if we may not understand those interactions well. And this is particularly an issue when the systems get larger and more complex. Integral architectures have some advantages also. It generally increase product performance and reduce cost for a specific model. The downside of that is they don't develop very good platforms. The arrangement for this is as follows. If you give me a particular design, I can probably eliminate some interfaces and share some functions. This will probably reduce cost and improve performance, but reduce flexibility. This is an example of an integral product. It is an Olympus compact camera. I can imagine that to change this from the zoom model to the cheaper non-zoom model probably requires changes in many different components in order to achieve that high performance, that compactness. Compared to the SLR camera, you may swap lenses easily. This is a product that some of you may recognize. It's a Ford Taurus. It has what they called an integrated control panel. It came in old models, years actually, over 15 years old. They had an oval-shaped theme. They used it in rear windows, headlights, and control panels, as you see here. They called it integrated control panel because this panel actually runs the radio system and the climate control system. What your comments about this design? It limits the ability of consumers to make some changes. You certainly cannot buy an aftermarket radio, for example. You need to change the climate controls to change the radio. The reason I brought this up because there are two divisions at Ford that were involved in the development of this control panel, the climate control group and the electronics group. Traditionally, these two groups did things separately. The climate control people did things that did not have to deal directly with the electronics people. To create the integrated control panel, that required a lot more interactions between the two groups, more than what they are used to. These interactions are different and than what existed. The point is that the choice of architecture dic- dictated new kinds of interactions that were really hard to do because they were not used to doing them. The message is program management issues or constraints may in fact dictate the architecture you choose. Here is a summary of the issues considered when deciding between integral and modular architectures. The first two kind of go together, product change and product variety. They both are intended to create variety, but the difference is product change is created by the user and product variety is created in production. Product change, for example, we produce the product using modular architecture and the customer makes some modifications to it. For example, they change the copier toner or swap camera lenses or renew the blade on the razor. We can create the variety in production too. Classic examples are computers, where you have different disk drive sizes or screens, etc. Automobiles also another example where you have different colors, radios, sunroof, no sunroof, etc. Hundreds of combinations are possible. Standardization. Very few people design and build things like motors, bearings, and fasteners to use in their product. I could very easily pick these out of a catalog as standard parts. I also have to adhere to standard interfaces in my product architecture. That allows me to use these catalog components. I may choose to separate that in a separate chunk. For example, a motor may be separated as a separate chunk to provide torque function that you choose a standard part for. On the other hand, we might actually build special bearings to use in high performance products such as racing bikes or fighter jets. So integral products are usually used to improve performance. Manufacturing cost is another issue to consider when choosing between integrated and modular architectures. If I have a single product to produce, I want to choose an integral architecture to reduce production costs. If I have a family of products to produce, I want to choose a more modular design to reduce cost for the whole product line. Disk drives, for example, started with modular designs where the main components, the head, the arm, and the motor, were implemented separately with separate components. The need for cheaper and more compact drives emerged. These three components were later integrated into a single component in the new drive designs. Finally, project management and systems engineering. One of the benefits of carefully choosing a product architecture is to enable sensible decomposition into subsystems and chunks. If we have a modular architecture, it is easier to assign these subsystems to different teams for parallel development where the interactions between these chunks are well defined and understood. In an integrated architecture or integral architecture, this distributed team assignment may be a little harder because there are so many interrelated and interdependent things between the different teams. Here are three products: a Motorola cell phone, an Apple notebook, and a Ford Explorer. My question is, do these products have integral or modular architectures, and why? Let's start with the cell phone. It is lightweight and pretty compact. What do you think of the architecture? You may say integral because earpiece is the same as the display panel, mouthpiece is the same as the keyboard, and so on. The antenna is kind of built into the whole thing. In terms of developing that enclosure, we have to implement a lot of functions into that chunk. And you could also argue, on the other hand, that it is modular because we can use a different circuit board to implement different functionalities, like CDMA versus the SIM card version. We may change the software or ship with different software enabling different features. So it has some elements of modularity also, and it has some elements of integral design, which is how it gets the compact size and high performance. I think that's a fair characterization for it. Okay, now the Apple notebook. What do you think? Again, modular. You can argue for modularity, casing for color options. You can upgrade memory or hard drive, the usual stuff. But some of the integral features in the antenna for the wireless networking, it's actually built into the screen. You can start to see that in any real product, except for the really trivial ones, products exhibit both integral and modular features. So there is a whole continuum of varying levels of modularity and integrality. And for each product, we need to think carefully what modular features do we have and or do we want, and what integral features do we have or do we want, and why. The Ford Explorer, one of the misconceptions about the Explorer is that people think it is the same platform as the Ranger truck. It looks the same almost. It looks like the Ranger is a wagon version, similar styling. They don't actually share a whole lot of parts or even a platform. Technically in a platform, what really matters is what we invest in. To establish a modular architecture, the steps we follow is first we create a schematic of the product, then we cluster the elements of the schematic into modules and chunks, and finally create a rough geometric layout showing the modular architecture of the product. We will show how the method works using this DeskJet printer example. Here is a schematic of the DeskJet printer example. A schematic is a diagram representing the team's understanding of the constituent elements of the product. The schematic should reflect the team's best understanding of the state of the product, but it does not have to contain every imaginable detail. Also, the schematic will not necessarily be unique. This schematic is very similar to the function diagram that we have seen in previous chapters. However, this particular schematic contains both functional and physical elements, whereas functional diagrams usually contain only functional elements. These are some of the functional elements: store output and store blank paper, while some of the physical elements that have already been decided by the team is the print cartridge, for example. So once we have this schematic laid out for the product, we need to do the clustering. The challenge in the second step is to assign each of the functional elements of the schematic to a chunk. One possible assignment of elements to chunks is shown here using 9 different chunks. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Several other viable alternative arrangements are possible. At one extreme, I can use a separate chunk for each element, resulting in 15 different chunks. Several factors to consider when deciding whether to combine two or more elements into the same chunk are, for example, geometric integration is one of them, which is assigning elements to the same chunk allows a single individual or group to control the physical relationship among the elements. Another reason would be function sharing, which is when a single physical component can implement several functional elements of the product. These functional elements are best clustered together. Another reason to consider is capabilities of vendors. A trusted vendor may have specific capabilities related to a project, or in order to best take advantage of such capabilities, a team may choose to cluster these elements about which the vendor has expertise into the same chunk. Another reason to consider is similarity of design or production technology. When two or more functional elements are likely to be implemented using the same design and or production technology, then incorporating these elements into the same chunk is desirable. Finally, a geometric layout is created. Here's one for the DeskJet example, showing the position or location of the major chunks or clusters. This process forces the team to consider the feasibility of the interfaces between the chunks. Another way to define the product architecture and determine the chunks or modules within the product architecture is using the dominant flow heuristic. The dominant flow heuristic uses a function diagram, which we've seen in the previous chapters, and the flow of material, energy, and signal within that function diagram. The heuristic is as follows. It says to define a module, follow a flow, whether it's material or energy or signal, from the point it enters the system until it leaves the system, or until there's some conversion within the system. Conversion, let's say, from electricity to heat. So then this will constitute the boundary of a module. In this example here, you see that this material entered the system or entered the block diagram, the function diagram, and it includes these subfunctions: this, then this, then this, then that, then this, and then it leaves the function diagram. So from entry until it leaves, this will constitute a module. That's the dominant flow heuristic. Let's look at an example. Let's apply the dominant flow heuristic on this example. It is a Black & Decker power cordless screwdriver. In the power screwdriver, the flow electricity passes through 5 subfunctions as outlined by the dashed rectangle shown here. The subfunctions store electricity, supply electricity, transmit electricity, actuate electricity, and regulate electricity are all combined into a single module, which is called supply electricity module. The next flow to trace is the bit module, is the bit flow. It first enters the system and traces through the 2 subfunctions, couple solid and couple secure solid. This set of subfunctions forms a module that we call coupling module. The flow hand right here identifies a superset of the coupling module, which also encompasses the separation of the bit from the device. The flow torque right here emerges from the convert electricity to torque subfunction and travels through the subfunctions change torque, transmit torque, rotate torque, and dissipate torque. Here the heuristic identifies these four subfunctions as transmit torque module. For the power screwdriver, the dominant flow heuristic identifies four modules, one for each purely sequential function chain. Finally, product architecture choices define the subsystem and modules of the product. Architecture also determines ease of production variety, feasibility of customer modification, and system-level production costs. The key concepts that we took out from this chapter is how do we choose between modular versus integral architecture, and how do we find clusters or chunks within the product architecture.